Hello and welcome. Today we're going to be taking a look at how to create an object detection model using TensorFlow Lite Model Maker, specifically for use in the First Tech Challenge for LAUSD. But this tutorial will cover how to create an object detection model for any use. In the First Tech Challenge this year, you'll note that your robot is able to visually detect specific objects on the field on one of the three spike marks on the field. And depending on the location of that object, tells your robot what it should do. Feel free to check out Game Manual Part 2 for more information about how to maximize those points. So what is TensorFlow? This is the software we're going to use for our machine learning. It is free and open source software that allows us to essentially teach our computer how to recognize specific things. And our TensorFlow Lite Model Maker is going to simplify the process of creating this mathematical model that can take input from a camera and output what object it believes it's looking at. So we're going to be able to use a custom data set that you're going to make yourself, and it'll use what's known as transfer learning to reduce the amount of training data required and shorten that training time, because creating one of these object detection models from scratch actually takes a lot of computing power and a lot of time. So the very first thing you're going to need is to record a video. Instead of taking thousands of photos, recording a video essentially does that. So it's a good idea to read up on selecting your team prop for this year's competition, reading about the best way to record that video. Essentially, what you're going to want to do is make sure that you record your team prop at different angles with different objects, possibly of the same color or different colors, and also record that video in the location and in the setting that your robot's going to be viewing it in. So essentially setting up your video as if it is the robot looking at the objects it's going to look at. Now, depending on the frame rate of the video you take from your phone, a 40-second video at 24 frames per second should make around 1,000 photos, and that should be plenty enough to train your model. All you need to make sure of at that point is ensure the video's format is either MP4, MKV, 3GP, AVI, M4V, MOV, or WebM. And if your camera or phone doesn't make any of those formats, there's plenty of online converters to use. We're going to be doing something called annotating our data. So in order to train the object detection model, you need to analyze each frame of that video and label it or annotate it with the objects you want the computer to learn how to detect. So to do this, we're going to be using a different technology than we did last year. We're going to be using a website called Keeley Technology. They allow a free account with up to 5,000 of these annotations, which should be more than enough for this project. So after signing up for your free account, what you're going to do is create a project. So let's go ahead and do that now. So you'll note they have a bunch of tutorial projects, but this video should fill that place. So we create a project and give it a name. I'll call it FTC. And under asset type, you're going to click video. And then we'll click continue in the right-hand corner. Now we're going to add our assets, the data that we want to annotate. This is going to be the video of your team prop. Now, you'll want to keep it the native frame rate. We don't need to mess with that. And we will annotate as a video instead of individual images. And you'll see why. That'll make this process a lot faster. We'll click upload. Awesome. So after it uploads, we'll click continue. And then we're at the edit interface. This is where we are going to tell Keeley Technology what type of labels are we going to be making. So we'll click new label job. And then select, out of all the options under object detection, we're going to click bounding box. This is the type of annotation that the TensorFlow Lite Model Maker is able to process. So bounding box. We don't need to add any labeling instructions if we don't want to, but we are going to add a category name. This is what they call a label. This is what we're going to call the object we're going to put this box around. So in my training video, I'm just going to be training how to recognize this blue stapler on my desk here. So I will call it stapler. Press enter. We don't need to add a second label in this case, but if you want to be able to detect more than one object, you would add a label for every object you're going to label. So we'll click continue. Under the add members section, we don't really need to add any other members unless you want to have a team of people. With this free account, you could have up to 5 members annotating or labeling your data and double checking each other as well. We'll click finish to create our project. And we'll add it to our queue. Now that it's here, we're going to click on our training video to open up our labeling job. So I've taken a rather short video. Your video is going to be longer. It's going to be in the robot field. What we're going to do is go to the first frame where we have our object. Here it is, right there, that blue stapler. And what we're going to do is choose the bounding box option near the top left. This is going to allow us to draw a box around the object we want to label. So we will draw that bounding box. And you'll note right off the bat, it has added this label, stapler 1, to about 100 frames of our video. What's nice is, instead of labeling or drawing that box around every single frame of our video, what Keeley has done is allowed us to use the arrows on our keyboard and just move through those frames one by one. And every time there's a major change in the box, we can click on the box, move it, or even resize it by using the dots in the corner and reposition that box to more accurately fit our object. We want to try and reduce how much other background objects are in here. And you'll note between the frames that we've changed, you can now see that Keeley will automatically interpolate or move that box for us frame by frame. It'll track the object a little bit for us. So we'll go a few more frames until it's not in the box anymore. We'll move the box back over, keep going, some more frames. We didn't move it much there. Now you'll note we've come to the last frame that has our label. If we go to the next frame, there's no more label. If you need to extend that labeling, you'll note at the bottom in the timeline here, if you click near the end of it, you get a little resizing bar and you can just add more frames for that label. And we'll do that. And what you're going to do is go through every frame of your video like this. And when you are done, just click the submit button in the top right hand corner. Now that your video is done being labeled, we're going to export our data. So to do so, you're going to click the ... menu near the top right hand corner and click export all labels. You can give that a name if you'd like, but the most important part is to select the label format. The format we need to select is called Pascal VOC. That is the format that the TensorFlow Lite model maker is going to accept. And when you click export, it's going to give you a notification that it's going to take a minute or two to export. What it's going to be doing is taking your video, splitting it into individual image files for you, and exporting all of the information about the labels. You'll note you'll get a notification up near the top right hand corner, which you can then click the download button. The next step in our process, now that we have our data prepared, is to really start working with some code. So to do that in your Google Colab environment, we're going to connect to a Google computer. So when we do this, we want to click this drop-down menu and ensure our runtime type is correct. So this says what type of processor do we want to run this code on? What we want to do is run it on a GPU. So when you do that, you'll click Save. You'll see T4 written here, and then you'll click Connect. This will connect your Google Colab Notebook to a GPU on the back end in Google servers. Now the first piece of code we're going to work with is connecting all of this to your Google Drive. So the first step will be selecting a folder name. All your data and all your models are going to be saved to your Google Drive account, so nothing stays in the Google Colab Notebook, but it will be housed in your Google Drive. I'm going to call mine TensorFlow 2024. And then as soon as you have that name, all you need to do is click the play button. It will ask you to authorize the connection to your Google Drive account. Please note that this will not delete any of your Google Drive files or folders. It's just going to be adding more. And after it is done connecting, you'll note it'll say that your Drive account is mounted. That way, our Google Colab Notebook can see the files in your Google Drive. So the file you got from Keeley will be a zip file. You need to unzip it and then upload all those files and folders to your project folder in Google Drive. And I've gone ahead and done that here. This is what it will look like. My project folder was TensorFlow 2024. And then I've uploaded all the files and folders here. There'll be an images folder, a labels folder, a README from Keeley, and a video meta.json file. So now that we have our files uploaded to our Google Drive, our code can read all of that data and work with it. So a big change to last year's code. Last year, Google Colab was able to actively run our code the way it was, but there's been a major update to Google Colab. Instead of using Python 3.9 as it did last year, they've upgraded it to use Python 3.10, which now the TensorFlow Lite model maker no longer works in. There is a breaking change. So to make this all work again, we are now going to have to actively force a virtual environment for Python 3.9 to work in, essentially just tricking Google's computer into running the right version of Python that we need to get this to work. There's a few steps. First, we need to set what's known as environment variable to tell it where Python's going to be located. Then we're going to install a piece of software called Miniconda. During this installation, it is going to require that you type the letter Y to agree to install the software. Now, this does not install any software on your computer. This is doing an installation on a computer over in Google's server farm. So you don't have to worry about that. So let's click the play button here and it will install our virtualization software. After about 30 seconds or so, you'll note a list of new packages that will be installed. And if you scroll down, you'll notice that a question has been asked. Should we proceed? Y for yes, N for no. And you need to click just after this question mark into a space, and you'll type on your keyboard the letter Y and press enter on your keyboard. That will tell the computer that yes, you're agreeing to install the software on Google's server. And now it is installed. Now we're going to add Python 3.9 to that virtual environment. First, we need to import and append some information about what version of Python we want. And then we're going to create that virtual environment with the correct version of Python. Again, when doing this, we're going to need to type the letter Y to agree to do this. And you're going to click right after that question mark for an input box, and you'll type the letter Y for yes and click enter on your keyboard. And now that that has been installed, we are going to move on and prepare our software to run our object detection model. So first step is to grab a script that I wrote that will do the actual training. This is the code that is going to run in that virtual environment with the correct version of Python. Feel free to look at the code in there. That's what's really doing the heavy lifting in the object detection training. For now, we're just going to download it. And that will download that file to Google's server, not to your computer. Successfully downloaded. Now we're going to install all the software needed to create our object detection model in that new virtual Python 3.9 environment. And this might take a few minutes to do. Finally, after a couple minutes of installing, you'll note it's going to install one final piece of software, which again will require you to type the letter Y to agree to the installation. So again, I'll click to the right of that question mark to get an input box. I'll type the letter Y and press the Enter key on my keyboard. And after a few more seconds, our software is now installed. Green check mark in the corner. The final step in this process will be to ensure that we have all the folders created in our Google Drive that will house all of our training data. This code will remove old training data. So if you have run this process before and you're trying to redo this process, it will get rid of any training, validation, and testing data that you've already created. You'll note if you don't have those files, it will warn you it can't remove them. That is perfectly okay. It will go ahead and still create all the new folders you'll need to do the training. And now we can begin the training of our object detection model. First, we have a couple options to select. The first option is about image downsizing. So when we took these images, my phone recorded that video in 1080p, like most of your phones will. That image is going to be prohibitively large for the object detection model to train with. So what we're going to do is downsize our images and the corresponding annotations we made for that size of image. A good image size is 240 by 240. If you feel like your model isn't as accurate as you'd like it to be, slowly increase this size as you try creating the model again. I do suggest you keep it in a square. That is easier for the object detection model maker to do its work. So we're going to click Run here, even if you want to keep the default size of 240 by 240. There we go. Now we're going to select a model architecture. So the TensorFlow Lite model maker works by taking an already programmed object detection model and building a layer on top of it. So the architectures we could choose from are called the Efficient Det for detection, Lite version 0 through 4. If you'd like to look at this table about their file size, their latency, how long it takes them to take in a single frame of data and provide the output, and their average precision. We're going to start with the Efficient Det Lite version 0. This is the fastest. The CPU on the robot controller hub isn't very fast, so this is going to run the fastest. It won't have any lag time, but it's also going to be the least accurate in that detection. So there's a nice sweet spot in between depending on how well you have trained your model and labeled it versus the architecture we choose here. So I'm going to choose the Efficient Det Lite version 0 and click the Run button on the left. Now we're going to go through and train the model. This step will take some time. It could take anywhere from 20 minutes to an hour, depending on how many images it has to go through. So here are some notes about what are going to happen. The first thing that will happen, it's going to take your data and split it into 3 different groups. It's going to randomly select 80% of your images and use those to do the training. Then it's going to take 10% of your data and use that to verify the training. So during the training process, it's going to use these 10% to ensure that it is making its way towards understanding the objects it's trying to detect. Lastly, another 10% will be used to evaluate the model after it has been created. Then the object detection model will be created. And you'll note the output of the code will go through epochs. These are different steps through the process. Your training will go through 50 epochs, which means it's going to go through the training set 50 times. It's going to look at that training data images and go through it 50 times. You might also see the word batch size during that. That is the amount of images that will be looked at any given time. So in this training, your batch size will be set to 8. After the training is done, you'll note that there will be some statistics printed out on the page. Feel free to click this link to look at the different model metrics that you will see and what they represent about the accuracy of your object detection model. At the very end, it will export that object detection model to your project folder and then do one final evaluation on that model using the test data set that has been created. So we're going to click this. This is going to prepare all the options that you have selected previously about your project folder, the new X and Y dimensions of your images, and the model type that you have selected. Lastly, we're going to run the object detection model training script. Again, feel free to see how that training script works by clicking the link to this GitHub. It's important to remember that this process will take time. Please make sure your computer is plugged in. This is the part that will utilize that Google GPU to increase the accuracy and decrease the amount of time this training will take. At the end of this process, you will have a file in your Google Drive folder called model.tflite. And that is what we're going to use to detect our objects. Now we can go ahead and test our model. To do so, we are going to first download our model and the labels file that came with it. So we have labels.txt and model.tflite. These are the two files that we need. Once you've downloaded them, we're going to upload them to this Google Colab Notebook. It's not going to run off of our Google Drive at this point. So to do so, we'll click this Run button, and we're going to select both the model and the text file. Please ensure that they are named model.tflite and labels.txt. Now that our files are uploaded, we can load the TF-Lite model evaluation functions. Feel free to look at this code if you'd like to see how it works. What it essentially will do is take in the model and the labels and some input and figure out how to draw a box around the objects it has detected. So if we just click Run, it will load that very quickly. Now we could take a test picture from our webcam. Feel free again to look at how this code runs. But what happens when we click play is it will open up your webcam. And then show you the output of your webcam. You can hold up or position your camera how your robot will see that object. And you'll click the capture button. Now that we've taken our picture, we want to test that picture with our model. So we need to select a detection threshold. This is a decimal number that represents the percentage that we want to set as the minimum for what it will detect. So when the object detection model sees an image, it's going to figure out what's in it based on what you've trained it. And if it has an inference, a prediction that something in the image is at a 50% chance of being an object, it will display that for you. If you set this higher, it will only show more confident predictions. So say 70%, and you can go anywhere from 0%, 0.00, or 100%, which would be 1.00. Now that's going to be very unlikely. We're going to keep it at 0.5 just to get a feel for what it's detecting and how accurate or how sensitive it is to detecting this object. We're going to click run, and we'll note it did not detect my stapler. This is most likely because my training data was very short, not well lit, and not at very many angles. I only took about 7 seconds of training data. You need more. Again, about 1,000 photos works really well. So you should see something detected. If you're not, and you've had some good training data and labeling done, so lowering our detection threshold to maybe 10% will allow us to see if it is in fact detecting this object just at a very low percent chance or low confidence level. So I lowered it to 10%, and we can see here, yes, indeed, it did detect the stapler. Note that my bounding box isn't covering the entirety of the stapler, and my detection level seems to be about 30%. So it's fairly low and is not sure if in fact that is a stapler. It did get it correct. Bounding box isn't covering it all, and the prediction level's very low. And so that has to do with a couple of different factors. That is because my training data was very small. I only took about 200 frames of video. You're going to want to hit around 1,000 to have a good data set. I also use the Efficient Det Lite version 0. That is the fastest running model. However, it is also the least accurate model. So you could play around with those options, play around with how much training data you're giving it, which model architecture you're going to use, and you might get some different results. Finally, there's one other way to test your object detection model, and that is testing it outside of Google Colab, which is going to be much more robust. So to do so, you're going to need to make sure that you have Python running on your computer, and you're going to need to download the files from the GitHub that is linked here and run the model tester program. Once you have this code downloaded, there's really just a couple steps. It's going to walk you through how to install the TensorFlow software to run on your computer. And as you can see, it will do live detection on the fly, so you can test your model much faster. Note that there will be a delay. Hopefully you have a fast enough computer that delay will be brought down to maybe 30 or 40 milliseconds. The reason for the delay in this example is that I'm also recording my screen at the same time. And now that we have fully tested our model inside and outside of Google Colab, your job is then to use that model in your robot controller hub. So to do that, you'll just need to verify that you have the latest version of the robot controller application that runs on that Rev Control Hub. You can download it here. For instructions on how to do the coding, please see First Robotics website if you're using Android Studio or the OnBot Java or even the blocks. I'd like to thank everyone who has helped me compile all of this code, and especially give thanks to Google, who has made the TensorFlow Lite Model Maker Object Detection Library and the original Google Colab Notebook that this is based on. If you have any questions, please let me know down in the comments. I will try and answer them as quickly and as accurately as I can. If you find any bugs or errors, let me know, and I will update the code as needed. Thank you so much.